Welcome to the third installment of our series on the FFT. By way of quick review, the first installment we created a noise reduction patcher using the PFFT object. In here we took our real and imaginary signals in the frequency domain. We checked against a threshold on the magnitude of the different bands of frequencies in the FFT, and then we either attenuated them or let them pass through. We then also made an FFT equalizer, much like the Forbidden Planet example in Max. In our second session, we rewrote that patcher. Instead of using the PFFT object to handle all of the messy details, we handled it ourselves. That means that we did an overlapped and offset FFT, and we windowed the input. This windowing function basically fades in and out. That way we're crossfading the input between these two FFTs so that the edges of those 512 bands are not sharp and they're smooth and they don't add noise. We then process each of these different quote-unquote voices which are happening in the FFT, and then we do an IFFT. Again, it's offset by 256, which is half the size of our FFT because we have two FFTs happening. And then after we've applied the window, we add the two overlapped FFTs together. So that's where we ended up. There are a couple of questions left and a couple of details we glossed over, but it's difficult to understand those when we can't see what's happening inside the FFT. So let's build a patch where we can start visualizing what's happening inside the FFT and use the FFT to visualize our audio signals in general. To get a handle on what's happening with the FFT and to do our initial visualizations, it will be easiest for us if we step away from Max, where things are happening sequentially in the frequency domain, and if we think about the frames of the FFT and the frames of what we want to analyze, and we'll just work in terms of pure numbers or lists. And we're going to do that. We'll actually use jitter to accomplish it. So let's start building the patch together. And to make this patch, we're going to start with a jit.matrix object. Now, often the jit.matrix we think of as representing a two-dimensional matrix in the case of video frame. In this case, we're going to just use a one-dimensional matrix, which is to say it's a vector of numbers or a list of numbers. And we'll first give this a name. So we're going to call this source. Then we tell it how many planes we want. We just want one plane of data. There's nothing fancy going on here. And we need a data type. So either float 32 or float 64. And then we need the dimensions. Again, this is just a one-dimensional matrix, meaning that it's just a list. We just need to give it a length. It's going to be 512 samples long. So that list is now represented in this matrix. If we want to take a look at that real quick, a real easy way to do that is with the jit.cellBlock object. We can hook that up. We'll send a bang to our matrix, and we'll see now there are 512 samples in there, all set to the default value of 0. So let's fill this matrix that's our source with some sort of audio wave. To do that, we can use an Uzi object, and that Uzi object can run through a sine function. So if we do that, we know we are going to have 512 values. The Uzi object starts counting at 1 instead of counting at 0, but jit.matrix starts counting at 0. So we'll go ahead and subtract 1 from this index as it comes out. That means that the range of numbers here is going to be between 0 and 511. So if we want that range to be between 0 and 1, we would divide by 511. Now that we've done that, we'll want to take that number and feed it into, for example, a sine function or a cosine function. But the sine function will expect that we're going to feed it values between 0 and 2 times pi. We're not going to be super precise here. We'll just go with quick and dirty. So if 3.14 is approximately pi, 6.28 is 2 pi. So we'll multiply this value, which is in the range of 0 to 1, by 6.28. And then we can go ahead and use a join object. This will make a list out of our index and our value from the sine function. That list can feed this jit.matrix using the set cell method. So we do set cell $1, which will be the coordinate within the vector, and then the value, which will be the second item in this list. Okay, so if we click this bang, a bunch of values get filled in here. If we want to visualize those values to see that this actually is a sine wave and not just some kind of goofy numbers, then one way we could do that is we could use a multi-slider object. It's kind of the quick and dirty way to look at a list. So we'll do that. We're going to need a trigger object from this matrix. And what we'll do with that trigger object is we'll use the jit.iter object. This will go through each and every item in this matrix and spit it out as a float. But we want to collect it into a list. So what we'll then do is we can use the ZL object in its group mode. We're going to be using some pretty long lists here, and the ZL group, any of the ZL objects, default to having a maximum size of 256. I'm just going to up it to 1024. We can up it further later if we need to. So now every number is going to pop out of there in sequence, and when it's all done, we'll send a bang to it, and a max list will pop out. And we can pump that into our multi-slider here. So if we do that, hit the bang, sure enough, we see a sine wave. If we want to see more than one sine wave, then we could hook up this number here, and we could multiply this here in front of our 2 pi multiplication. Okay. And we'll go ahead and stick a comment in here, and this comment is going to say cycles of sine wave. So now if I were to change this to 3, we're going to see 3 cycles of the sine wave. We should see 3 cycles of the sine wave if I hook up the patch correctly. We can hook this up to the bang so it automatically updates. Okay, so now we have 3 cycles of the sine wave. And it's actually 3 cycles of the sine wave per 512 samples. Okay. I'll go ahead and move this down here. A couple different ways of visualizing what we have going on. So now that we have a jitter matrix, we can use the jit.fft object, and we'll run an FFT. The FFT is going to be the size of the matrix that's passed in. So we have 512 samples. We'll do a 512 point FFT on those samples. And when we do that, hit the bang, we'll see here that we have some bins with numbers. We can see that this bin has a much higher number than the others, and then a whole bunch of zeros. And at the end, there's something different. Again, to visualize what's going to happen in this FFT, we could go ahead and do something similar to this over here so that we can see what's happening inside the FFT. If we do this, though, it's not actually going to be very intuitive. Remember, the output of an FFT provides a complex number, which means that it's a number in two parts. There's a real part and an imaginary part. So what's coming out of this jit.jitter is actually a list of those two parts. If you remember, to get the magnitude of the frequency bins, we have to take those two numbers and feed them to a cardipole object. So let's go ahead and do that. This is outputting a list. We can unjoin the list, break it into its two parts, which will be the real and the imaginary. Then we're going to hook it up to the cardipole object. Then that cardipole object will output to the ZL group. And now we have something in this that we could work with. It's a little bit hard to see, so let's maybe make some modifications to our multi-slider. If we come over here, one thing we could do is we could change the color to be a bit bolder. We can also change the range of the multi-slider to be more appropriate for the data we're looking at. We'll just make it from 0 to 1. And we can also make the style of the slider, instead of being these little pinprick points, we can make it a nice bar. Okay. I'll move this frequency up. So if we look now, what this is showing us is that there are some bands with nothing in them. Then there's a band here very near the beginning, which spikes up nice and high, and then a whole bunch of bands with nothing else in them. If we increase the frequency of this sine wave, we'll see that the band moves gradually. We'll see that the band moves higher and higher. We'll also see that there's another phenomenon going on, which is that there is another frequency showing up all the way over here on the right side and moving its way left in a mirror image. So what is going on with that? It turns out that anytime that you have a source for your FFT, which is a real number, which is what we've been feeding into any of our FFTs, the corresponding FFT will contain two halves, and the second half will be a mirror image of the first half. If we think about these frequencies, and we comment this appropriately, we start at 0 hertz all the way over here on the right. We go up to our Nyquist frequency. If you remember, our Nyquist frequency is the sample rate divided by 2, and that'll be in the middle, and then this is our sample rate all the way over here, our 44.1. So in fact, because this is always a mirror image, it's not usually doing us a whole lot of good. And so typically, we just cut this in half and don't use that mirror image. If we jump back to the first couple of FFT tutorials, I glossed over this point. I said in this FFT equalizer that we had 512 bands. Well, it is true there are 512 bands in the FFT, but actually, we're only processing 256 audible bands, because those 256 bands are these bands that go up to Nyquist. The other 256 bands are simply a mirror image. If we don't want to see these mirror image bands, we can just chop them off. We can do that here. We'll take a ZL group, we'll duplicate it, and then we'll modify it to be ZL slice, and we'll say we only want the first 256. And now, when we hit the bang, we'll see the spectrum as we expect it. We can shovel this all down a little bit, make some room. And now, instead of going up to our sample rate, this goes up to Nyquist, which is sample rate over 2, or in this case, 22 kilohertz. There's another way we can visualize all of this, and that is to use the plot object. If you remember the plot object, it provides a way to take a list and draw a two-dimensional representation of that list. If we use the prototypes, we can get a long ways without having to do a lot of work. So if I choose the audio scope, for example, I can take this list of 1024, and now we can see that this contains a whole lot of sine wave cycles. Similarly, I can use another plot object, and I can tell it that I want to see the prototype which says that I have a spectral plot. We can use decibels versus normalized frequency, or decibels versus hertz. Each one has its own advantages. For right now, I'll just say decibel versus normalized frequency. Normalized frequency meaning that we have 0 at this end. The normalized frequency of 1 will be the Nyquist frequency. And then we can hook up this list over here. And what we'll see is a visualization that is just like this visualization over here, except that this needs to have the number of points changed to match the number of points in our FFT. Let's change that attribute. Num points, we can change it to 256. Now if we change the number of cycles here, we have 10 cycles per 512 samples. We can see that visualized here in a multi-slider or here in the plot. And we can see the spectrum visualized over here in this multi-slider or again over here in the plot. The plot gives us this advantage that we can see with much greater fidelity what's happening at these lower numbers. There are actually numbers here. If we go to the cell block, it looks like it's a lot of zeros until we get to the bin that has energy in it. But if we take this and we find the inspector and change the precision shown in those numbers, we'll see that actually there are values all throughout here. And those are what we're seeing here in this plot object, down around negative 72 dB. Again, if we change this frequency to 20 cycles per 512 samples, we'll see that this is moved, and if we then change it again to being, let's say, 200 cycles, we'll see that we move all the way up toward the top end of this, knowing that this represents between 0 and 256. If we want to think about this frequency in terms that are a little more comfortable to us, instead of thinking about, say, 20 cycles per 512 samples, we could think of how many cycles per second. That would be very useful. So how do we figure that out? Well, let's make a floating point number box up here. We're going to say we're going to have the cycles of sine wave per second, which is another way of just saying hertz. And we take that, we will divide it by our sample rate, which in this case is 44,100. We can hook it up to a DSP state object to make it generic and work with any sample rate. Then we can take it and we can multiply it by the size of the FFT. And then we'll feed this into this number box over here. So now we could say something like 100 hertz, and we'd see that it's this many cycles per 512 samples. Or if we changed it to being 2000 hertz, we would see that it's equivalent to this number of cycles. At this point, because we're specifying this in hertz, we could go down here and change the plot object and use a different prototype. We can use the dB versus hertz. And now, when we set this frequency, we can see that this is going to show us right here, there's a peak at 2000 hertz. And again, if we drop this down to, say, 600 hertz, now we can see that there's a sine wave generated down here or up here. That sine wave has the FFT performed on it, and it produces a chart that shows us that there's a frequency at 600 hertz, knowing that this is 200, 300, 400, 500, 600, right here, right on that line. So this is pretty cool. We have some signal coming in. In this case, we're looking at it as a list, but we have something coming in, and we can find out what the frequency is that's coming out. If we had a more complex wave, we would be able to see the components of that wave. So let's go ahead and add some additional frequency components to this wave and see how that applies down here. So what we can do, after a little bit of tidy up here, is we can make another sine wave, and then we'll add those two sine waves together. And then those two sine waves that we add together will be what feeds our FFT analysis. Let's go ahead and also hook this one up to the bang so that when we add this frequency. Okay, so now we see two frequencies. We see both of them showing up in our analysis. We see them both also showing up down here in the multi-slider. One thing that we could do is we could scale these so that they each have a gain. That would be useful to do. So let's give each of these a gain. We'll say this sine wave is multiplied by 0.5. This other sine wave is also multiplied by 0.5. And our patch is getting messy. We'll tidy it up in a moment. Now when I calculate this, we can see our wave without clipping. We also see that the level of these two peaks has been reduced. But there are questions. Well, at least there are questions for me. One question that we have is about the gain levels. These are showing gain levels that are down around negative 12 dB. And that is even though we've applied a gain here, which should not yield that large of a drop-off. I'm going to go ahead with this cell block, and I'm going to put it back to a precision of 2, just to make it a little clearer what's happening. We have very low level values here until we find our peak. Then at the very end, it mirrors itself. So here's our peak. 0.24 is one of our peaks. This other peak is at 0.31. Why are they those values? Well, this is showing us the real component, not the imaginary component, so this isn't necessarily the magnitude, but those values are not quite expected. And the reason for this is a bit technical, but the FFT is designed to operate on complex numbers. So it can take a complex input, meaning that it has a real and an imaginary component, and then it produces a complex output, which means that it has a real and an imaginary output. We've been looking at real and imaginary outputs. That's what we operate on down here with our cardipole object. But the numbers we're feeding in do not have an imaginary component. They're considered what we would call real input to the FFT. The jit.fft object normalizes as if it was always receiving an input, which is a complex number. But in this case, it's just a real number, so it's not actually normalizing the FFT in quite the right way. As a result, everything is off. So we're going to compensate for that normalization in this FFT. I'm going to build a vexpr object here. If you aren't familiar with the vexpr object, it's an expression object which operates on vectors. So we can take $f1, which is to say the first inlet is going to be a floating point inlet, and we're going to take that number, and we're going to multiply it by 2. And then I always put the scalar mode in if that's what I'm intending, which it is, which means that we're going to apply this multiplication of 2 by each and every element in this vector. Okay, so we're going to apply that to both the real and the imaginary that's coming out of this jit.iter. At the moment, if you're feeling a little bit overwhelmed about this new concept of normalization of the FFT, we'll talk about it in just a few moments when we normalize FFTs ourselves. For the moment, I'm just going to leave a little comment here. Okay, now when I trigger this, we'll see that this gain comes back up. Our peaks are up here at about the negative 3 dB level, which is exactly what we would expect. There's another question that commonly comes up, which is when I look at this spectrum, and I know that I have two frequency components, and I see those two frequency components are very strong, but then I see all these other frequency components here, all along here at negative 36 dB, and then here trailing off. They aren't just at this frequency. In the multi-slider, we can see that this frequency has these long tails as well. So why is that? To explain that, let's go back to the frequency calculator that we used in one of the earlier videos in this series. And so what that did is we took a number, which we said was the bin, or the band number in the FFT. We take that bin number and we're going to try and figure out what frequency is represented by that bin. To figure that out, if we remember, we have a DSP state object which will provide us with our sample rate. And we'll be able to bang the DSP state and find out what exactly our sample rate is. Then we're going to divide that by the size of our FFT. In this case, that's 512. And that's going to tell us the size of our band. So each band is of the size 86.13 hertz. So if we multiply this number here by the size of our band, we'll find out the precise frequency represented by each bin. So bin 0 represents 0 hertz, or DC. Bin 1 is 86.1 hertz, and onwards. Up here, bin 7 represents 602.9297 hertz. So what happens when we have a frequency, in this case 600 hertz, which isn't exactly this frequency? That is one of the questions. If I change this here to 602.9297, we see a small change. The bigger change will come when we go up to this 1400 hertz, because we're further off. Okay, so the nearest bin for that is either bin 16 or bin 17. If we come here and enter 1464.25, now when we look at this, there is no tail coming off of either side of this. When we look over here in the plot object, which gives us a lot more detail, we see that this trails way off, and we don't have nearly as much showing up in the spectrum on the sides. So what we're seeing in this case is that frequencies that don't land precisely on the frequency of the band or the bin in the FFT, they end up smearing. And so what we see when we have an imprecise frequency like this 1400 hertz is that those frequencies end up smearing out across all the other bands of the FFT. One way to compensate for that is with windowing, and that's the reason that we window. We'll come back to that also a little bit later in this video. So I'm going to save my work, and I'll go ahead here and do a quick save as for this work. I'll say part 3B. That way we can shuffle some of this stuff out of here and take a quick look at a few other concepts. One place we can start is we can get rid of our sine wave generators here and look at a couple of different input signals. We can hack some of these out of here. We can get rid of this. And let's see what some noise looks like. Well, noise is really just a random number. We can make this anything we want, and then we can scale from 0 to 4095 to -1 to 1, which would be our expected range. And then get rid of all of this. So if we look at noise now, we can see that indeed we have a noise signal, and the noise produces more or less random output in the frequency spectrum, but that it's pretty uniformly distributed. If we were to look at silence, silence is simply going to be putting out a 0. And so if we put out silence, which is flat here, here is just going to be nothing. If we were to put out a click, right, which is a single discontinuity, so I just patch up the equivalent of what Max's click tilde object would do. And the click tilde object basically puts an amplitude 1 spike, which is 1 sample long. So this click produces a spectrum where all frequencies are perfectly evenly distributed across that click. And that's one reason why if you get some sort of click or discontinuity in your audio, it's so hard to get it out. It's because it occurs at every single frequency across the entire spectrum. Another thing we could take a look at here is we could look at a phasor. How would a phasor work? Well, if we took this number here and we divided it by some number of times that we wanted to see a ramp occur over for a frequency, then we could do a modulo of that. We could say modulo 2 because we're going from 0 to 1, but to make an audio wave we need to make it -1 to 1, so it would have a range of 2. And then we could shift the whole thing down by 1. Oops, down by 1. This will give us a phasor with 14 cycles across our 512 samples. And then we can see over here what this looks like. Why does this look a little funny? Well, what you'll see is that if we change this frequency, and I'll go ahead and bang it every time we do that as well, we can see all kinds of nasty stuff in here happens. It's not just like a nice pure sawtooth wave with a bunch of pure frequencies, and those pure frequencies with silences in between the harmonics. What we're seeing that this is a non-band limited saw wave, like the phasor object in Max. And as a result, there's all kinds of aliasing. And that aliasing folds back a lot of frequencies into the audible spectrum. So if we get up to, say, 16, there's 15. 15 doesn't look too bad compared to the way some of those look. But if we get to 16, we can see the frequencies show up. And there are no frequencies in between. It just drops completely out. The reason for that is that anything that gets folded back in is going to get folded back in this case, directly onto the same frequencies that are already present. So let's take what we've accomplished here and what we've learned in this domain with where we can work with the lists, and let's apply it to an audio signal processing path. To do that, I'll go ahead, we'll make yet another patcher. We'll make part 3C. We'll get rid of all of this. And I don't think we'll need that either. And so to visualize the FFT, we're going to come in. We'll take a look at the audio input. Easy ADC. This is going to analyze the sound of my voice coming in. So now we want to perform an FFT on this audio signal. To do that, we can say we're going to have an FFT. We could make it any size we want. I'll say 1024 this time. Get a little bit more frequency resolution, and we're not going to have any offset. To keep it simple, our first version will not do any windowing. Now that we have our FFT, we need to find out what are the magnitudes of our bins. So we're going to use a car-to-pull object. In this case, we're in the signal domain, so we need the one with the tilde. Okay, so we take the real and the imaginary. That's going to produce a magnitude over here. We want to take a look at it here in our plot object. So we can drag our plot object over. 256 points isn't going to be the correct number of points anymore. We really want to have 512 points because remember, 1024 represents both the spectrum up to Nyquist and also a mirrored spectrum from Nyquist all the way on up to the sampling frequency. So we've changed this to 512 to match our FFT size. Then we can hook this up and turn this on. And what do we see? Well, I'm talking, and every time I talk, the numbers go completely off the chart. Why are these numbers going way off the chart? Well, this comes back to the normalization that we talked about in the JIT FFT. We mentioned that the JIT FFT object was doing some normalization internally, and it was doing that based on the idea that it would have a complex number input. Well, the FFT tilde object doesn't do any normalization internally, so we need to do the normalization ourselves. If you're using a complex signal input, which means if you were feeding in a real input here and an imaginary input here, then you would need to divide by the number of bins in the FFT. Because we're only doing the real input, we can divide by half the number of bins in the FFT. And that will give us our normalized signal. And the thing that we're normalizing is the real and the imaginary components. So I'm going to divide, in this case, by 512. It needs to be a signal version. We'll do this again for the imaginary. So normalize. And when we do this, we'll get numbers that look more reasonable because it's normalized and it's in the appropriate range. So now when I'm talking, we can see the results of that. And if I make some S sounds, you can see that those are higher frequencies than the O sounds. So this is all fine and dandy. If we, instead of using my voice, we could use some sort of synthesizer. That would produce a reference that we could understand a bit better. So if we take a saw object, and I'll give it an initial frequency of, say, 2000 hertz, because that's easy to see on our plot object. Okay, so now we see the saw object, and it's putting it at a frequency at 2000 hertz, and then here are each of the harmonics from that frequency. We're also seeing that there's a bunch of stuff in between these, as we saw before. And we mentioned that this is because the frequencies are showing up as smeared between the bins. And the way that it shows up like that can be reduced with windowing. So let's make a windowed version. If we're going to make a windowed version, an easy way to do that right now would be just to copy and paste from the previous examples that we have in this series. So if I go back to part 2, I can come over, find our FFT noise reduction patcher, and we know that we're going to start out with this half. That gives us our FFT, that gets us our window applied, and the whole 9 yards. So we can take all of that and come over here. We can paste it here. Maybe it would make sense to put this in a subpatcher, so we can do that. Say new patcher windowed FFT. Paste this in here like this. Ultimately, what we're going to want is an outlet. Okay, so we're going to feed our saw into the windowed FFT, and then whatever it is that comes out of here, we'll go ahead and hook into this other signal for the plot object, which will plot with this red line. One other thing we need to make sure we grab from this other patch is we're going to need to grab the buffer that actually contains our window. So we'll go ahead and stick that over here. So in our windowed FFT, we know from our previous experience that we're going to need to normalize this FFT. So first, let's fix the size of this FFT so that it's the same as the other. So we're going to go ahead and say that this is going to be an FFT 1024 with an offset of 0. The other FFT that we're going to be overlapping is going to be 1024, but with an offset of half, which is to say 512. Then we're going to need to normalize these outputs from the FFT. So we'll divide by 512 with the signal rate division. If you're worried about the optimization of that division, because you're savvy and you know division takes longer than multiplication for computers, internally Max will convert this because it's a constant and will actually be performing multiplication. So we've normalized these frequencies. Then we can run our magic cartipole to get the magnitudes. Okay. Now that we have the magnitudes, we can go ahead and we can sum the magnitudes. There's one more detail we'll have to come back in here and deal with in a second, but first let's look at how this works. Okay, I'm going to turn this on, and it doesn't do anything. Why is that? Because the FFT window is not filled in. Size and Samps, we'll fill it up with a Hanning window. Okay. Now we can see the blue one, which has no windowing. We can see the red, which has a Hanning window applied to it. We can try out the different windows now. For example, if we don't apply any window, it's the same as what we would call a rectangular window. We'll see that it's essentially the same. If we apply a Hanning window, it knocks down all of these frequencies in between the important bands. If we apply a Blackman window, it gives us a slightly different shape where it transitions more sharply and then levels off. There are a whole host of different windows we could use. And the question could be, well, why use one instead of another? Well, that's largely dependent upon what sounds best to you in a particular scenario. Often, Hanning will be the default. That's certainly the default in Max's FFT in and FFT out objects in the PFFT. A Blackman is quite often used in the cases where you're doing 4 overlaps or 8 overlaps or more. Hamming and Hanning are very similar, but have a slightly different profile to them. Ultimately, you can use one of the defaults, or you can experiment to see what's going to sound best. It'll vary with your different source material. But now you have the tools with which to visualize how those windows will affect your sound. And you also have some additional background on that. So let's turn this off real quick. We've covered a lot of ground here. We've talked about everything from the frequency smearing. We've visualized FFT responses in the control domain using JIT-FFT. We've seen the impact of windowing. We've seen the mirrored spectrum. So just take some time to digest all of this. If you poke around at the FFT objects a bit more, some of this might start to make sense, and some of it may just take some time. But as an example, when you make a PFFT object now, we're armed with more information. We know the subpatch name, we know the FFT size, we know the overlap factor from previous videos. Now we understand the full spectrum flag. If we turn that on, we'll get the mirrored spectrum. By default, it's turned off because we typically only care about the first half of the spectrum, which is from 0 to Nyquist. So armed with all your new knowledge, you can now patch away. And the next time we get together, we'll get to talk about more of the practicalities and some tricks for doing FFT processing to make it sound really good. Until then, happy patching.